Okay, stat students, we're going to go ahead and try this out. We're going to go ahead and look into um, distributions of data. So a distribution of a variable is the value that a variable takes and how often it takes that value. So when we're looking at our distributions, a lot of times we're looking at graphs like a histogram or a dot plot. We're kind of looking at the shape of them. And when we're working with quantitative data, we can actually calculate the position in the distribution by calculating what we call the percentile of that value. The percentile consists of the percentage of values that lie below that particular value. We do not include that value in our calculation. So percentile should be written as whole numbers. So if you get a decimal, you need to make sure that you're using your rounding rules. So we have a sample problem here. We have a stem plot that shows the number of wins for each of the 30 major baseball league teams, Major League Baseball teams in here. And so right now, I just want to go ahead and underline this to point out that we're talking about 30 teams. So we've got 30 in all. And we're going to find the percentile for specific teams. So the first team we're going to look at is the Colorado Rockies, and they won 92 games. So when I look at them, they are this number right here, that 92. So I want to figure out how many numbers are actually below that. So I'd go through and I'd count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And I don't include that 92. So I've got 24 numbers below out of 30 numbers total, and that's going to help me calculate my percentile. Now I could have also counted how many numbers were above. 1, 2, 3, 4, 5. Add in the number that I'm including, that's 6. And so then I could subtract from 30. 30 minus 6 gives me that 24. So now I'm going to go ahead and take my calculator. I'm going to divide 24 by 30, and it's going to give me 0.8. Which translates into my 80th percentile. For some reason my pen's not working very well. Okay, so now we're going to go ahead and we're going to calculate for the Yankees. And we are told that the Yankees won 103 games. So when I look, 103 is the very top one, which means there should be 29 numbers below it. So this should be 29 out of 30. Which is 0.9666, and it just keeps on going as a repeater. So this is, we round it to the 97th percentile. I don't know why my pen's being such a butt. Okay, our next one is we are doing the Kansas City Royals and the Cleveland Indians, who both won 65 games. So when we're looking at how many numbers are below 65. And that is 1, 2, 3 numbers below, so 3 out of 30. Which is 0.1, which is the 10th percentile. And there's a lot of times where they will ask you to interpret your percentile. And we interpret this by saying that if it's the 10th percentile, 10% of the teams are below that. 97th percentile, 97% of the teams are below that. And it would seem kind of weird based on example B. You would expect that to be 100% of the teams, but you can't really include themselves in it. So that extra 3% above is themselves. So not 100% of the teams are below them, but 97%, whatever is left, not including themselves. Okay, also in chapter 1 we talked about frequency charts, or frequency tables, and that's when we were doing the counts, how many people or individuals fit in that certain category. And then we talked about relative frequency charts, where we have a proportion, or we turn it into a percentage. But now we're going to start talking about cumulative frequency charts. So how many altogether are below our value? And so it's kind of going in line with that idea of percentile. So we have a table showing the distribution of median household incomes. For the 50 states and the District of Columbia. So in our income range, we have 35,000 to 40,000, and we have one state in there. So one out of the 50 states and DC area gives us a relative frequency of 0.20. Now cumulative frequency, we still have the one. Actually, it's just one. I don't need a one out of. And then for the relative, now I'm actually calculating the percent. So 1 out of 51, which is the 0.02. Now as I move up, I'm going to start adding it together. So in this one, how many altogether are below? So now we have 11. So when I calculate the cumulative relative frequency, I'm talking about 11 out of 51. Which gives me an ugly decimal. I'm going to go ahead and round it, 0.22. So about 22% are below that value. And then I keep adding on. So I'm going to add a 14 in there. So 11 plus 14 gives me 25. And I'm just going to keep on going. And then I'm going to add the 12 and the 25, gives me 37. The 5 and 37 gives me 42. The 6 and 42 gives me 48. And the 48 and the 3 gives me 51. And so this is how we get this idea of cumulative frequency or cumulative relative frequency. So then I still go through 25 divided by 51. .49, and then 37 divided by 51, which is 0.73 or 73%, and then 42 divided by 51, which is 0.82. And then we have 48 divided by 51. Oops. And then 51 divided by 51. Which gives us 1. And so from here, we can start looking at our median, which is about the 50th percentile. So right around here is my 50th percentile. And then I can look for my first quartile, which is about 25%, so somewhere in here. And I can look for my third quartile, which is about 75%. And so we've got mean, first quartile, third quartile. And you can use that to help you figure out some of this information. So then we also have a graph of this. So this is a cumulative relative frequency chart. And I can actually determine my 5-number summary from here. So I can look at, for my 5-number summary, what's my lowest value? So I look at 0, which is 35. Keep hitting that button. That's 35, by the way. And then I'd find my first quartile, so about 25%. So 25% would be right around here. And that value at 25% is 45. And then for my median, I'm looking at 50%. And so at 50%, my value is 50. And then for my third quartile, I'm looking at 75%. So I'm going across, and that value is 55. And then I'm looking for my max value that happens at 100%, which is 70. And again, you probably want to use a measuring tool to make this a little bit more accurate, but you get the idea. We get our lowest value, our first quartile, our median, our third quartile, and our max value. So we're going back to that whole 5-number summary. Now, if I want to interpret the third quartile from the graph, then I would say 75% of the states have an income lower than, and now I'm going to go ahead and look at what is my third quartile. What is that 75%? And that is 55,000. Now remember, when you're looking at this type of graph, the steeper the line segment, the more values that are in there. So this is not as steep as that. So there's more values that lie in this range than in this range. And this is even steeper, so more values lie in here than they do over here. So the steeper the segment, the more values that are in that little area. Okay, so now another way to look at position is what we call a z-score, and this is a very, very popular way of figuring out, like, to be able to compare positions in different distributions. And so a lot of times we'll do this to compare SAT scores with ACT scores, because they have totally different scales. So what we do is we're looking at, with a z-score, how many standard deviations from the mean our value is. And so we look at that center for mean, and we look at the spread of standard deviations, and then we're looking at how far away that is. And so the higher above the mean, the better. The lower below the mean, the worse your score is. And so we're kind of getting an idea of that. Now, having a standardized location allows us to compare those different distributions, and typically we want to compare distributions that are of the same shape. So that's really important. The z-score is not measured in the same units as the variable. It is measured in standard deviations, because again, we're always looking at how many standard deviations away from the mean is it. It is also directional, where a positive z-score will tell you that it's above the mean, where a negative z-score will tell you that it is below the mean. And the number tells you how many standard deviations above or below. When we're looking at standardized scores, if you look at all standardized scores, they will have a mean of 0 and a standard deviation of 1. And a standardized distribution will have the same shape as your original distribution. So if your distribution was skewed to begin with, the standardized distribution will be skewed. If your original distribution was symmetrical, your standardized distribution will be symmetrical. So how we calculate z-score is with this formula down here. You take whatever value you're trying to standardize, you subtract the mean of the distribution, and divide by standard deviation. And so this is what it looks like in symbolic notation. I take the value x, I subtract the mean, which is x bar, and divide by the standard deviation. So in 2009, the mean number of wins was 81, and the standard deviation was 11.4. Find and interpret the z-scores for the following teams. So the New York Yankees had 103 wins. So I would take that 103, I would subtract our mean of 81, and I would divide by the standard deviation of 11.4. And so on your calculator, I recommend doing this in 2 steps. Do 103 minus 81, hit enter, and then divide by 11.4. Because if you're not careful, it will calculate it incorrectly. And I got a value of 1.92982. So what that number means is that they are 1.93 standard deviations above the mean. What is wrong with my writing with this pen? Okay, so now we're going to look at the New York Mets. And they had 70 wins. So I'm going to take that 70, I'm going to subtract the mean of 81, and I'm going to divide by the standard deviation of 11.4. So 70 minus 81, and I hit enter, then I divide by 11.4, and I do get a negative number. So it's negative 0.96, and so we are 0.96 standard deviations. I'm going to go ahead and shorthand that. Below, because it was negative, we're below the mean. Okay. So 2 basketball players are arguing about who is a better player. One is a top rebounder that averages 12 rebounds a game. The other is an assist leader with an average of 8.7 assists per game. The distribution of rebounds per game has a mean of 11.3 and a standard deviation of 1.74. Oops, that's supposed to be rebound, so that's supposed to be pink. And I just still did not get pink. So for our rebounder, I'm going to go ahead and label with R for rebounder. To find their standardized score so we can compare rebounds to assists, we're going to go ahead and take the amount of rebounds they had, 12. I'm going to subtract the mean of 11.3 and divide by the standard deviation of 1.74. So 12 minus 11.3, and then I divide by 1.74, and I get a value of 0.40229885. Okay, now we're going to go ahead and take a look at that assist leader. So the assist person, they have 8.7 assists per game. And the mean for assists is 8.1. And the standard deviation is 1.47. So we're going to take that 8.7, subtract 8.1, and then divide by 1.47. And I get 0.40816. So who is actually better? Well, they're both pretty close with standard deviations. They're about 0.4 standard deviations above the mean. But the assist leader is actually a little bit higher. So I would say the assist leader is the better player. Now, of course, they have different skills, but in regards to assists, which is the strength of the one player, they rank higher than rebounds, which is the strength of the other player. And so they're lower, they have a lower standardized value. Okay. Okay, so we have one more problem, and this one actually comes straight from an AP exam. I can't remember the year, but I want to say it was around 2008 or so. The characteristics of speed and strength are considered of equal importance to the team in selecting a player for the position. Based on the information about the means and standard deviations of the strength and speed data for the two players and the measurements listed in the table below, which player should the team select if the team can only select one of the two players? So it's down to player A or B, and we're going to go ahead and we're going to figure out how they compare with strength and speed. So we're going to go ahead and do speed first, and we're going to look for speed for player A. So player A has a speed of 4.42. I'm going to subtract the mean speed, which is 4.6. And I'm going to divide by that standard deviation of 0.15. So I get a negative 1.2. So they're below the mean by 1.2 standard deviations. Okay, so for player B, I'm going to go ahead and I'm going to calculate the speed for player B. So player B had a speed of 4.57. I'm going to subtract the mean, 4.6. And divide by that standard deviation. So this guy's a little below, but not by much. So player B actually has a higher score than player A. So when it comes to speed, player B is better. But I also have to look at what's happening with the weight and strength. So for player B, let me go back to that same color. So we're going to talk about weight or strength for player A. And player A can lift 370 pounds. The mean is 310. And the standard deviation is 25. So we're going to calculate how many standard deviations away they are. So I subtract, hit enter, then divide by that standard deviation. So player A is 2.4 standard deviations above the mean. Pretty good, pretty high. Let's go ahead and look at player B. So the weight or strength for player B, well, they lift 375 pounds minus 310 divided by 25. And they have 2.6. So it looks like player B kind of has it. Player B has it for the weight. They are stronger. But when I actually think about this in context, for speed, you don't want to be above the mean when it comes to speed. You don't want to have a higher time. You actually want a lower time. And so this person actually has the faster time. So they actually kind of win there. So I was actually incorrect because I didn't really think about that when it comes to speed, you want to be below. You want a faster time. You want a lower time when it comes to running. So now we're going to look at, well, one wins with speed, one wins with weight. And so that's where we're always needing to think about this in context, not just numbers, but in context. So let's think about who's going to be the better pick. So in our picks, we have weight, which this is 2.4 and this is 2.6. This person is better by 0.2. But here, this person is better by 1 whole standard deviation when it comes to speed. There's not a huge difference in their weight strength, but when it comes to speed, person A is a lot faster than person B. And since there is such a big difference here, person A would be the person to pick. Okay, so we'll be practicing this type of stuff. We'll be doing z-scores all chapter. So you'll be seeing it over and over and over, and the more you think about things in context, the more it can get confusing, but it also gives you better information about the situation. So take time to think about that, and don't make the mistake I did by just rushing through and looking at the numbers.